So my name is Charles Fan, and I work for a startup company called the Memory-Converged. We are about 2-year-old, and we focus in developing software on top of storage class memory. And I used to be a developer, but then never a very good one, and now even worse. So you will now see a lot of source code in this presentation. But I think what we are doing is somewhat interesting, so it should be a good session. And I'll save 10-15 minutes at the end for Q&A, so that we can go into what we do. Okay, so the title is Adopting Persistent Memory, or Storage Class Memory, in the new Memory-Converged Infrastructure, MCI. And that's sort of the category of technology that we think we are creating. And so I'll start from the customer problems that we are trying to solve with our product. We focus on data infrastructure, with data-centric applications, and this is catching people's attention over the last 20 years, but even in the more recent times, because the Internet of Things, just the volume and the velocity of data continue to increase. And now, on the cloud side, on the data center side, to support the increase in the volume and the velocity and variety of data, that people have been building various frameworks to handle the influx of data. But there have been two fundamental bottlenecks. One is on the storage side, we are limited by the latency of the existing storage media, where NAND flash has been the state of art. So in a typical storage subsystem, we have a latency of about hundreds of microseconds, and that's sort of the best of class storage system you have. And in some of the cases where people are demanding faster response, more real-time insights from the data, and in those cases, there are some solutions that are memory-centric, where the data is being placed into DRAM, and where you can have nanosecond response time or latency. But DRAM has its own limitations in the sense of capacity and cost, and also it is volatile. So you have an okay solution for big data. If you don't care about the speed so much, you can just have more and more servers and more drives and to handle the petabyte scales. Or you can have a solution for fast data, as long as it's not big. You just put them in DRAM. But there is not a good solution if you want to deal with big and fast at the same time. So that's really the gap that we see. If there's a demand from customers to have a solution that can deal with data that's both big and fast, to the extent that they can enjoy nanosecond speed together with petabyte scale at the same time. And people have been working towards this, but there are just physics that's in the way, the underlying media that doesn't allow you to have such a solution until today, that we have now the emergence of a new class of memory, that's a storage class memory. And I think we all know about this. Intel shipped the Optane DC persistent memory earlier this year. And that's based on the 3D crosspoint technology. And we have information, rumors, et cetera, that there are other companies working on similar alternative technologies. And we expect by 2022, there will be at least 4 or 5 companies making storage class memory that can serve both as main memory that can be accessed in byte addressable way, and that as well as persistent, that it can survive power cycles. And this market, we expect to be a new significant market over the next 5 years. I think there have been some industry analyst prediction that by 2023, Intel will sell $3.6 billion of their 3D crosspoint storage class memory. Now, I think with a conservative estimate, with the DRAM market being $100 billion today, if you just take 10% of that market, That's a new $10 billion market, starting from zero today. So in the next 5 years. So we think that's a pretty exciting new market that is in the process of being created. And now the key driver or key blocker for the creation of this market is really how the applications, how the software ecosystem going to respond, and how the developers going to embrace or not embrace this new technology, whether the new programming paradigms, as some of the other talks has been going through, are going to be adopted by the applications. And we all know that's not simple. There are many applications today running in data centers, dealing with data, and to re-architect an existing application is not a simple ask. So Intel Optane memory now support 3 ways of accessing it. You can access it in a memory mode, which is backward compatible to DRAM. So the OS just sees it as a bigger and a bit slower DRAM. So you do not have to change your application. And so that your application can enjoy a bigger memory space, up to 6 terabytes for a 2-socket server. But it cannot enjoy the persistence capability of the memory if you operate it in memory mode. You can also operate it in block storage mode, where it just appears like a block device, 4K read and write. In that case, it's a faster device than the SSDs, and it handles read and write and persistence, but you really cannot access it in a byte addressable way and use it as memory. So in those 2 backward compatible modes, it can allow the memory to be used, but not really fully utilizing the benefits this new hardware provides. The 3rd way, or really the way Intel would like us to use it, is AppDirect, where you can take advantage both of the persistence and the byte addressability, but that does require you to program to a new API. And the existing application would not work without a rewrite of the application. Now, the new application can take advantage of it. If you're writing a new database, you can certainly design it well, that your table can be placed in this persistent memory, that it became much more attractive. You may not even need a storage engine anymore if you design your transaction engine the right way. But it's not so easy to rewrite your existing database, existing big data platform, existing machine learning platform to this new API. So that's where we come in. Really, MemVerge, we are focusing on creating a layer of software that can help the adoption of this new hardware by existing applications, as well as future applications. So we call ourselves a memory-converged infrastructure. We're essentially a middleware, if you will. We are being installed onto a set of servers that runs Linux, and that has this SCM inside of servers. And we have 3 main components in our software. At the bottom is what we call a memory hypervisor. And this is not a x86 hypervisor. It doesn't virtualize your CPUs, but it virtualizes your persistent memory. We access the persistent memory in AppDirect mode, the 3rd mode, so that the application don't have to. So they can continue to access volatile memory as volatile memory, access storage as storage, and they can program to it if they want to, so we can support the persistent memory API as well, but they don't have to change their application to start using the persistent memory underneath. So we essentially a translator. We access the persistent memory in the AppDirect mode, and we present memory and storage APIs to the applications so that they continue to work. The actual data actually lands on the same physical pool of persistent memory, and we can deliver larger memory, faster storage at the same time, and we can save on the IOs between them as well because they are already landing on the same physical media. So that's a powerful concept. I think having this virtualization layer on top of persistent memory while supporting existing applications. But we didn't stop there. Behind those 2 APIs, the volatile memory API and the storage API, we built 2 additional subsystems. Behind the memory API, we build a distributed memory system. This essentially, through our software, we can tier between the DRAM in the system, the local SCM in the system, as well as the remote SCM in the cluster across the RDMA link into a 3-tiered memory system, so that the available memory to an application is beyond the 6 terabytes available locally, and it's also accelerated by the DRAM that's existing in the system. So that's a SCM native distributed memory system that we created on top of this hypervisor. We also created, we believe, the world's first SCM native distributed file system. In fact, I have Andy to thank for this description. It's the first distributed file system that's designed for storage class memory, for the memory speed that the underlying media operates at. Now, we all know this is certainly not the first distributed file system. There are maybe 26 other distributed file systems out there, both open source and proprietary. But to our knowledge, none of them are designed for memory media. They were designed for hard drives. Some of them have been optimized for the NAND flash SSDs. But memory media, storage class memory, starting with Optane, is 2 orders of magnitude faster in terms of latency compared to the previous NAND flash media. So it does require different assumptions being made as we design the algorithms for the distributed file system. And we took many of these different considerations, and we basically developed this distributed file system from the ground up for the SCM. So it is a combination of these 3 software components that we created our product. We entered beta in July, so we are testing it with a number of beta customers, and we are planning to GA it in Q1 next year. We don't have a name for the product yet, so if you have any good names, you can suggest to us. So you'll have a name of the product. But essentially, this is what it does. It combines those 3 key software components, virtualizes underlying SCM, and supporting existing applications, and really building the bridge between what's running a data center today and this new wonderful hardware that's coming out, and offering larger memory, bigger storage, and more efficient I/O between the memory and storage without requiring application rewrite. So this is putting it into a data center that you have a bunch of servers underneath, and these can be just regular x86 servers that supports SCM. So if it's Intel servers today, the Cascade Lake CPUs or later will support the Optane DCPM, data center persistent memory. Now, in addition to the SCM, we also support DRAM and SSDs in the system, and these servers are interconnected, as I mentioned, by RDMA networking. We can support up to 128 nodes, 128 servers in this cluster, and our software is being installed on each of these servers. The applications can be installed in 2 ways. They can be installed right on the same servers that our software are running and where the SCMs are located. This is sort of a hyper-converged way of deploying your applications. They can be also deployed on servers that is a network away. We recommend RDMA connection to those servers as well, but they can be separate servers from where our software sits. So there's plus and minuses with these 2 types of deployments, and also depending on the customer environments and their applications. And we focus on 3 type of applications to start. I believe, let's say in 10 years, all applications in the data center can benefit from this new hardware media and our layer of software. But today, with generation 1 of the hardware, it is still at a relatively high cost. And so we are starting with the subclasses of use cases that we can demonstrate persuasive ROIs to the customers. And these are the few use cases that we have identified, and it's actually just subclasses of these use cases. Machine learning is actually a bigger field, and there are many types of machine learning problems. And we have found some subclasses of machine learning problems that can really benefit from the combination of the persistent memory and our software. And namely, these are the machine learning problems or tasks that has a higher data density, meaning the amount of data movement or data I/O to the amount of the CPU calculation, that this ratio is high, so that the bottleneck is more on the data interface between CPU and memory, or CPU and the CPU, GPU and memory, CPU, GPU and the storage. When that's become a bottleneck, our solution can really help accelerate. Some examples of these models are recommendation engines, which I'm actually going to go into a specific example, where the model is very big. So you need to keep writing to this very big model, and the training data is also large, and the layers is actually relatively shallow, so the computation complexity is actually not that high. So, and there's another example when NVIDIA introduced this RAPIDS framework, where they had tried to perform so the more of the work inside of the GPU with the data preparation, data resizing, adding noises to the data, and all the preparation work, the pre-processing of the data before it actually goes into the DNN training. And that actually implies a lot of data movement for these pre-processing to take place. So that's another example where our solution can be a good fit. So there are quite a few sub-cases of machine learning that are very good, that we can demonstrate a very good ROI for the customers. The second category is the big data analytics. Typical platform we're working with, a Spark, Presto, Hive, etc. And some of these are memory-centric, that we can enlarge the memory space that allow those applications to run. And almost all of them have a lot of I/O. Even for the Spark or Presto, which runs things in memory, they still have a lot of I/Os that interact to their storage subsystem, whether it's local SSDs or whether it's HDFS system. And our system, in addition to the memory enlargement, can also accelerate I/Os as well. So we can do both for those platforms. And then we are also having some use cases with the RocksDB and MySQL, the KV store, database type of workload, that we can accelerate those as well. And then now we are working with some banks for their low latency market data analytics, trading applications, that this can provide a low latency infrastructure that was not possible before without the SCM, storage class memory. So those are the first use cases that we can deploy our MCI into. And there are multiple ways these applications interface to our product. We have on the memory side, we can intercept transparently the memory allocation functions, so that we can manage the allocation of the applications in a transparent way to the application. We can also have a client library on the memory side. If the user have control over the application, they can decide what to use our MV malloc to our system, what they still want direct access to the DRAM without us taking over all of the DRAM. So we have flexibility, either no application modification, or they can use our client library with some small functional calls that they can have higher granularity access between the different memories. So that is the access on the memory side. On the storage side, we support, we use the optimized version of Fuse to have a local mountable file system. So anything that's writing to a local SSDs or local file system can just use our local mountable file system at a pretty high performance into our system. We also have an HDFS compatible API, that anything that writes to HDFS can just be redirected to write to us as well. In some of our initial use cases in machine learning and big data, between those two APIs, we can basically do everything that they need to do on the storage front. And for the fastest, highest performance storage access, they can also link to our client library and access our storage subsystem directly by calling our function calls. So that would be an option where they, again, make some small modification to their application and to get an even higher performance level. So those are the APIs, the ways they can access our system. And the initial customers, or beta customers, we found tractions with our solutions are largely in three different sectors. The first sector are some of the hyperscalers, the internet service providers, cloud service providers. They actually were among the first customers we work with, started last year. Now we are also working with some financial customers, some banks and hedge funds and exchanges, and as well as the HPC and AI companies that we're gonna, I think the first conference we're gonna have a booth gonna be the SC19 conference that we're gonna be hopefully talking to some of those HPC customers. So those are the sort of the first customer use cases that we are going into. So now let me start talking about a couple of specific use cases, how it is being deployed for a couple of different customers in their data centers. The first use case is with AI training, and this is with a large social networking company who has a recommendation engine that recommends to its users what other users they might know and they might want to connect to. And it is a pretty large service with 600 million users and over 10 billion connections between those users. And so it's quite a bit of training data actually collected from various data sources. And it's using a model that was invented at Google called wide and deep. It has some deep layers, but mostly it's a very sparse and big, wide model of this machine learning training task. And it's using a distributed cluster of servers. It has a couple dozen servers and running TensorFlow with this model. And it's using local drives for, or before us, it's using the local drives for intermediate temporary data. And the actual training data is being placed on HDFS. And that's where it gets the training data into the training farm. And the problem they have is, number one, the training takes a long time to complete. It takes days, if not weeks, to complete a round of training, and where they hope this can be accelerated because there are constantly new users, new connections. An updated model would give you better predictions on the right recommendation to make. And also because it's long running, the risk of failure is more costly. So if you have a node failure, you have to restart from the very beginning of training. You may just lose a few days of machine time, data center time, and restart from the beginning again. And a way to prevent against it is through checkpointing, where you can save all the parameters or weights of this model onto the persistent storage once in a while, so that if you have a failure, you just restart from the last checkpoint. But the checkpointing itself is expensive given the size of the model. So that if you turn on checkpoint at good frequency, then you slow down your training job even more. So it's like they are kind of between a rock and hard place. It's difficult to have a fast training and a good fault tolerance during this job. So with our system deployed inside of this recommendation engine, we replace both the local drives and the HDFS system. So the training data is being imported into our system, serving as where the training data is stored. And as the training takes place, the intermediate data is being saved into our system as well. And by doing this, we basically offered 3 benefits. We increased training time by as much as 6 times. So what used to take a week now takes a day. and change. And then the data import can be dramatically faster. But this is not a surprise because HDFS actually doesn't perform very well when you do this type of importing jobs. So it's just because the pool performance of the baseline that we were very significantly faster. And now we can also turn down checkpointing at a much higher frequency so that its behavior in the presence of failures can be much more graceful. So this is the first example how our solution is being used for a social networking company. The second use case is for a big data analytics use case with Spark SQL. And this is actually with a cloud service provider who are serving a cloud data warehouse service on Spark SQL to their customers. And they actually have a pretty large Spark cluster, a couple thousand nodes. And the previous case, we can be deployed in a hyper-converged deployment. As I mentioned, the application running on the same servers. With this customer, because they have such a big farm that's already there, they are not, as much as Intel would like them to, they are not ready to replace them all with the new servers, with Cascade Lake and obtain DCPMs. So how we help them is that we can add a few servers with the storage class memory and with our software to the side of the Spark farm. So this is a disaggregated way of deployment, and they are interconnected by RDMA. And in this way, that we can really extend the memory footprint of Spark in case they run out of memory. And we redirected the intermediate data from those Spark clusters to our Memory cluster. And we not only didn't slow it down, we actually make it faster, make this whole Spark SQL job run faster. And they also have can enjoy the added benefits, which was a surprise to us. It was not by design. But for them, it's very important because now their intermediate state is being moved off their Spark farm so that their Spark cluster become more elastic. And this can shrink or grow more readily as their customer demand changes. So we have the benefit of accelerating some of the typical jobs as well as increase the cloud elasticity of their service. And we actually, I think with this, we actually presented at one of the earlier SNIA events earlier this year. We did it with Tencent Cloud, Sparkling Cloud Data Warehouse Services. So those are the two examples how our solution is actually being deployed into real customer use cases. As I mentioned, we are starting more, with the financials. Those are actually just getting started in the last 2-3 months. And so hopefully in the next presentation, we'll be able to share some of those use cases as well. So let me maybe conclude my sharing with a couple slides about the vision we have about the transition of the data center architecture driven by storage class memory and memory-converged infrastructure. So our view or our opinion is that 2025 will be a key year, and that's roughly 5 years from now. I think by that time, we'll have a pretty developed market in terms of this new class of memory that's being made available, and market size we expect to reach at least $10 billion. It's a conservative estimate. And enabled by these persistent memory, non-volatile memory, storage class memory, whichever name you call it, that we believe the data center will be increasingly memory-centric. So what do I mean by that? Is that today, if you look at data center, you have servers that has compute and memory sitting in the servers, and you could have a farm of those. And then you can have performance tier storage that today typically driven by flash drives. They can be either a custom storage system, or they could be a distributed storage software running on commodity, but they are basically there to deliver very high performance data persistence to the applications which are running on the compute and memory. And then you could have another tier of capacity-driven storage or capacity-tier storage, secondary storage, archives, backups, et cetera, et cetera. So that's more optimized for scale, for capacity. And that's the world we are working with today, and there could be various kind of networking technologies in this picture on the left. We think by 2025, there will be this new green area where we call MCI that's going to be powered by storage class memory. And it's going to be a much larger in capacity compared to the DRAM layer that's available today. And I think Intel just starting it this year. In the next 5 years, both from Intel and from the other vendors, we'll see higher capacity. For example, the Gen 2 of storage class memory going to double in capacity to 12 terabytes per server, and I think Gen 3 will further double that as well, and the cost will go down as we go forward. So essentially, that will offer at least one order, maybe more, in terms of the capacity of memory that's available to the applications. And it will also have persistence capabilities and software enablers built on top of it, such as a solution that we built, so that will make the primary tier storage obsolete. That you no longer need an active performance tier of storage, given that capability is already provided by this memory tier or by this memory-converged tier. So that's our sort of bold vision, is that with this memory-centric data center, there will be a disappearance of your primary tier of storage. And so this layer, I think the architecture, if you double click between this compute MCI, there will be new interesting stuff there also. And I'm sure we are hearing different talks about the new memory buses, the CXLs and the Gen Zs, the various fabric that's going to exist between the compute MCI layer. Both within the node or within the rack that's interconnecting between them. But between the compute MCI, all the active application work will take place. There will still be capacity of storage that will exist, that's where you dump your data to. But this green MCI will be a multiple of $10 billion of a market created from zero. And I think this is a huge opportunity for everyone involved, for both the hardware vendors, for the developers, software developers like ourselves. And we started 2.5 years ago, before we could get a first sample of the Optane or Apache Pass module, with this vision in mind. We're placing a bet that this will happen, and we are very happy to see Intel actually shipped this hardware earlier this year. So we are lucky to be a first mover in this space, but I think we will not be the only mover. I think there will be various solutions in this space really to create this new technology layer that we call MCI. And I think this journey really starts today with a version 1 of our Converged solution. As I mentioned, we support a cluster of up to 128 nodes, and it will offer both storage and memory capabilities. On the storage side, we can offer latency go down as low as 1 microsecond, and we can support throughput of up to 10 million IOPS, 4K read-write from a single server. And if you scale, and we have linear scalability as you're adding the nodes, so you can essentially get to billions of IOPS. Not billions, 1 billion IOPS across our cluster. And across this cluster, you can have a total memory capacity of over 700 terabytes available to the applications. So I think even the step 1 of this journey that will be available next year will be a pretty exciting new world that we present to the actual applications, and it can offer very new deployment options and performance levels that customer can enjoy from the data-centric frameworks they have. So we are pretty excited about this MCI, and obviously we are still working very hard. We're still in beta. There's still a lot of work ahead. But I'm very proud of the work we have done, and very happy to share with all of you here. So let me move to Q&A to see if you have any questions on what we're doing. Yes.
The slide before this one,
Yeah.
when you show that memory goes away, even now with Intel or all the persistent memory, you still need RAM. They still need RAM.
Yes.
I think RAM will ever go away.
No, yeah, I agree. So at least with the Optane, that we don't see that this will replace all of RAM. So underneath this green, MCI is a combination of DRAM and SCM. And maybe a little bit of SSD there also. So so it's basically a variety of hardware that this layer manages. But I do think there is a prediction in terms of there will be the SCM shipment going to go like this. I think the latest prediction I see is by 2029 is when the shipment of SCM going to eclipse the shipment of DRAM. So the amount of, at least in terms of volume, it will actually exceed. There's some prediction that this will exceed DRAM over the next 10 years. Yeah, DRAM I think will also continue to increase. It's just this going to go much faster, right? Yeah. I think there was another question there.
Yes. With your distributed memory module, I mean, if the application want some data to be cached in memory,
yeah.
Can the data be replicated across several nodes?
Yes. Great question. So right now, our version 1 will not support replication for memory services. So if you're using, so essentially we provide memory mode and storage mode at the same time. They're API, you can call them, they coexist. And if you're using memory, it will not be replicated because it's just slow it down too much. And on the storage side, we plan to support replication when we go GA with the product.
About storage part, do you mean the file system?
Yes, the file system part, yes. Yeah, so on the file system part, we do plan to enable the replication feature. Right now, it's not turned on in our beta. We are still working on it right now. Yeah. Yes.
If I'm intuiting what you said on this slide about performance tier storage, in my mind, that's today's NVMe, ZDS,
yes,
and that sort of tier.
Yes.
And I have not seen anything indicating that storage class memory is going to be taking on flash technology any time soon, or maybe ever. And so I don't see where that gets eliminated. Even with the transition to a fabric-based system like CXL, it seems like you're still going to have CXL bridges into the cheapest bit,
right,
which is,
right,
for the foreseeable future, still flash.
Right. So maybe let me clarify. I think this is a bit analogous to the earlier question. I do not think that storage class memory will replace NAND flash in terms of the hardware devices. My prediction, which I could be wrong, is that NAND flash will exist. Some of it will exist inside of that MCI. So as you see, our product that we have DRAM, we have SCM, and we have SSDs. And those are the NVMe SSDs. And how we manage those three tiers is we're using DRAM and SCM to enable the memory services, and we use the SCM and SSD to enable the storage services. So we have a two-tier to enable the storage services underneath the MCI. So NAND flash will still exist. Part of it exists underneath the MCI. And I also predict that in the capacity tier of storage, which today is HDD-centric, I think in 5 years, it might become SSD-centric. So there will be SSD, all flash secondary storage that's going to be out there, and those will be probably QLC, the cheaper storage there. So SSD will continue to exist, but they're just going to live in these new layers. Yeah. Yes. Sorry.
About your memory system, as you said, the application don't need to do any change, just link your library, right?
Okay, yeah.
So my question is, how do you choose? I mean, the memory system manages RAM and hub system memory.
Right.
So how do you choose?
Sure. Yes, I think I understand the question. So, so on the memory side, there are two ways of using our system. The first way, actually, you do not need to even link the library. I think we're using a method, LD preload, on the compiler side to overload the malloc new and all those functions. So we kind of take them over. And in that case, it is the benefit of this way is you don't have to change anything. Your application just run, but you are trusting us on exactly what do we place on DRAM, what do we place on the persistent memory, SCM. So this is the first method where we are taking over the whole thing.
But I think in your memory system, you need to do some optimization to make
Right.
your memory more efficient.
Yes, and that's the intelligence we built into our memory system, is for what do we use what. So that's sort of the,
To put hot data.
right. Exactly, that's the memory placement work that we do inside of our software. So now, the second way is through linking with our library, which we offer like another set of malloc, we call MV malloc, Memory-Converged malloc, which essentially you can, as a developer, so that does require some application change, but it's only on the interface side, so it doesn't really change your logic of your application. But in your allocating your memory, because application always knows it better than we can know, so they can potentially do a better job than we can to see what to place in DRAM, what to place into the SCM. So in that case, they can use the regular malloc call to use the regular DRAM and using MV malloc to allocate to our system. So this way we give the control to them. So we have two methods. One is the transparent, you trust us. The other is we give you the control, but you do have to link to our library and change a little bit of your program. So those are the two ways you can use it. Yes. Yes.
Yeah, you list the two usage models, right?
Right.
Storage, the other memory extension.
Right.
So if you have to make a choice between those two, which one you think will be more leading towards the future of the SDN?
Okay. That's a great question. I think today, you know, all the applications are written. Almost every application has they for sure use memory, and most of them use storage. Right? So today's application always use both, and we want to really address both. I think SCM, really the power or the attraction of it, the allure of it, is that it's the first. It's the first technology that removed this wall between memory and storage. And so that's through this single pool of media that we can address both protocols. And I think your question is whether customers sees more value in the memory side or the storage side today. So do we sell more to the customer that we're selling a bigger memory, or we're selling you a faster storage, right? And that's a great question, and we are still finding out. So we do have customers on both sides. So we have a few customers who are looking at us as a bigger memory primarily, and there are some other customers looking at us as a faster storage primarily, and there are some who are looking at us as both. And I think we are still early in this journey to tell. So this is one of the questions. I think I'll probably give you a better opinion maybe next year. All right, I think my time is up. Got some signal, so thank you very much.